Hi there, I'm John McMillan, and welcome to this edition of PCB Tech Talk, the podcast where we'll be talking about pads, the EDA industry, and the questions you're asking. I'll be bringing in special guests including subject matter experts, listeners, and EDA industry leaders. So be sure to subscribe to this podcast. Let me know the topics you'd like to discuss, and if you'd like to be my guest, right here on PCB Tech Talk. Today I'll be talking about what's typically referred to as the foundation or the building blocks for all printed circuit board designs. And if you haven't guessed already, I'm talking about the component land patterns, or footprints, or decals, or package symbols, which, by the way, I'm going to use the term land patterns for this podcast so we'll know exactly what we're talking about. Well, no matter what you call them, what really matters is that they're accurate, because if they're wrong and the PCB gets fabricated and a problem is discovered during assembly, you've just wasted a lot of time and money. You know, as a designer, I know we take things personally. You take it personally when things go wrong, not to mention your boss. You know, they're going to want to know what and why it happened. And you'll have to go into overtime mode, to make corrections and respin the board, which can be tough, especially if the error was in a high pin count device and there's a lot of constraints on traces and vias to maintain, and nobody likes going through this, but it can and does happen. So why does this happen? Are there ever errors in the datasheet? Yeah, I've seen that. And do people make mistakes? Yes. I mean, it's part of being human. And even automating the process can have flaws. So is there a process or procedure missing that could have prevented it? Well, that's very likely. The catalyst for some of the best design processes come out of learning from mistakes. I remember working on a design many years ago, and we used a particular manufacturer for nearly all our RJ style connectors. And they supplied data sheets that had both the mechanical part dimensions and the recommended land pattern, which is pretty typical. And every RJ we built to this point had the dimensions from the component, that's the mounting side, except for this one particular connector where the land pattern was mirrored. This mistake actually caught us in the prototype run. Well, fortunately, it was easy enough to work around for testing in the lab and simple enough to correct for the next build of the prototype. But any designer, or if you're in a big company with a librarian, will tell you they do not like it when things like this happen. I know I don't. Another thing that always stands out to me is when manufacturer data sheets list an industry package type for their component. Let's use a simple example of the SOIC. So right now you can Google SOIC 8, and you can find datasheet after datasheet with different dimensions, some subtle, for both the component and the recommended land pattern, even different tolerances. So to simply have a library symbol for an SOIC 8 is not always an option. And if you assume one land pattern fits all, you will likely get that call, the one where you're informed that the component pins extend over the land pattern, or the pads are too narrow, or the component body is obstructing test points or something else like that. And no one wants to get that call. What designers or librarians end up doing is creating land patterns that are specific to the manufacturer's part. But this can present other challenges. How do you create a land pattern for a component that has multiple sources of supply? That is, 3 different manufacturer brands make and sell the exact same functional component. All are described as an SOIC, but their component dimensions may be slightly different. Can the land pattern actually be designed in such a way that it does not matter which manufacturer is used? Which, by the way, the manufacturer for identical parts are typically based on component pricing and the availability of the part. Another consideration for land patterns is related to the environment for the component's use. For example, the IPC 7351 standard defines environments for most, nominal, and least, which means that for each SOIC8 land pattern we create, I'll refer to my default library land pattern as nominal, that 2 additional land patterns for that same component may be built. The most environment will facilitate designs that have no spacing concerns. They may even be subject to extreme vibrations or similar environmental impacts and require the largest suitable pads for the most robust solder joints. And the least is what we will see in our micro design, our handheld devices like cell phones, smartwatches, where printed circuit board real estate is at a bare minimum. And not only are the LAN pattern pads the smallest possible, but in most cases there is no solder mask deviation, and the silkscreen figures and reference designators are often omitted altogether. So we find ourselves creating an SOIC8 for different manufacturers as needed, and perhaps even 2 additional LAN patterns for every one of those if we happen to design a variety of different kinds of PCBs that are used in these different environments that I just described. That's a lot of LAN patterns. LAN patterns that need to be correct and validated for fit before the design goes out for fabrication. How do we ensure that the LAN patterns, the foundation, the building blocks of the printed circuit boards are correct and avoid the "I'm sorry but the parts don't fit" telephone call that you might get? Well, let's discuss some of the ways this can be approached and prevented. The first area I mentioned was datasheet errors. This is a real tough one. If you are working on a design and you have and particularly if you have to sole source a component, that is, there is no other supply source available, you have to make sure that if there is a recommended LAN pattern, that it is correct. You might find that using a tool like a LAN pattern creator that will enable you to enter a component's physical dimensions and calculate the LAN pattern is a great option. This way, you can compare the calculated LAN pattern with the datasheet dimensions and make corrections or modifications necessary to help you ensure that the part will fit when it comes time for assembly. The second area of concern that I mentioned was human error. This is also a tough one. Using a LAN pattern calculator, as I just mentioned, can result in the same errors that full-on manual LAN pattern creation is subject to. Even if a single dimension is entered incorrectly, even if you take a subtle typographical error in the 100th place, for example, and couple that with a minimum or maximum tolerance variation, can create problems in nominal conditions and cause even worse problems in the least environment. So how can we avoid human error? Well, a lot of designers build in a QA process that may include a peer review. That is simply that someone double checks your work, which works well, particularly in large companies with multiple PCB designers, which may even include dedicated librarians. Another way to possibly eliminate human error that is becoming more and more commonplace, not to mention it can save both the time and cost associated with building the LAN pattern yourself, is to acquire LAN patterns that have already been pre-qualified. Optimum Design Associates, for example, makes LAN patterns to the designer's specifications and guarantees 100% accuracy, and they're actually checked with Valor MPI for footprint accuracy. And I believe they can even create them as quick as 24 hours. By the way, if you're a Mentor Pads customer, here's some good news. You can actually download a library of over 11,000 parts created by Optimum Design Associates for free. And I'll post a link for that in the podcast show notes. I mentioned Optimum Design using Valor MPI a moment ago. If you're not aware of the VPL, which stands for Valor Part Library, I think it's really important to note that this is an amazing capability. The VPL library has more than 35 million component part numbers with accurate physical models. That is the physical component, the mechanical part I talked about earlier from the datasheet. So what the VPL does is it enables you to superimpose the physical packages with their pin contact areas right over the LAN pattern, just as it would look once it's been placed during assembly. That is, virtually prototyping the design before it goes out for fabrication, eliminating any component LAN pattern assembly issues. No matter if there's 1, 3, or more alternate sources of supply for the part listed in the bill of materials. It places them right on top of the PCB's component LAN patterns, runs all the checks, and lets you resolve any package to LAN pattern assembly issues or mismatches before the design ever goes out for fab. Valor MPI, by the way, is tightly integrated with the new PADS Professional solution. You can go to pads.com to learn more about that. There's no denying that incorrect lamp patterns can make or break a printed circuit board design, costing you both time and money that you typically don't have. We all want to get the product to market on time and not have it end up in the scrap pile. So taking steps like some that I've described in this podcast can help you to ensure that lamp patterns are correct and that the components fit during assembly. Well, that's our time for today. I hope you enjoyed this topic, and if you have something you'd like to share on this topic, I'd love to hear from you. And if you're interested, maybe be a guest on one of our future podcasts. As always, be sure to check out the podcast show notes. There you'll find the links that I refer to during this podcast, as well as my email address where you can send me your comments and questions and podcast ideas. Thanks for listening, and be sure to catch our next episode of PCB Tech Talk.